For the SCUDEM 9 challenge, we have developed a MASH model for bioaccumulation as a potential solution to problem A. A recent study has prompted concern over alarming concentrations of heavy metals in chocolate, particularly lead at 0.062 micrograms per gram. Long-term consumption could potentially be associated with bioaccumulation of these contaminants and lead to unintended health consequences. Even occasional indulgence can pose health risks, motivating the development of a model to demonstrate the long-term dynamics of the most prominent toxin, lead. Children are especially vulnerable to developmental delays associated with heavy metal toxicity and higher absorption rates. Toxin concentration modeling can aid with providing recommendations to parents regarding the safety of chocolate consumption. Heavy metals enter the gastrointestinal tract through consumption of contaminated chocolate. While some toxins are directly excreted in feces, the remainder are absorbed into the bloodstream and pose health risks. Toxins in the bloodstream circulate between hard and soft tissues at variable diffusion rates, dependent on the relative concentrations in each. Some contaminants are absorbed into the renal system and excreted in urine. Short-term storage is comprised of soft tissue organs, including the brain, muscles, skin, etc., while long-term storage is comprised of hard tissue, namely bones. Several assumptions were made during the modeling process. Chocolate consumption was modeled by a semi-periodic function with uniform contaminant concentrations. Bodily systems were grouped based on tissue type with no direct consideration for toxicity in individual organs. Absorption rates were modeled following the logistic curve, dependent on the relative species concentrations. For example, the absorption rate of lead from the GI tract in the bloodstream follows a logistic decay model dependent on the lead concentration in the bloodstream. Bodily volume is implicitly considered for the contaminant concentration in each system. No spatial effects influencing absorption or excretion rates were considered as the model is strictly time dependent. Contaminant concentrations in each subsystem, namely the bloodstream and soft tissues, were considered to determine the absolute toxicity and health risks following the basic toxicology principle, the dose makes the poison. Various ideas from the conceptual base were consolidated to develop the overall model block diagram and corresponding system of ordinary differential equations. The four bodily spaces of interest, the gastrointestinal tract, bloodstream, soft tissues, and hard tissues, were labeled as M, A, S, and H, respectively, with the ultimate goal to determine the contaminant concentration in each with respect to time. M was selected to indicate heavy metals, with A standing for absorption, hence the name MASH model. Respective absorption rates between each system were labeled as alpha, beta, and gamma, with F indicating fecal excretion, R indicating renal excretion, and P times C dot representing the consumption of heavy metals in chocolate. Based on the block diagram, the model was developed as a non-homogeneous system of four ordinary differential equations, written in matrix form for simplicity. As previously expressed, the absorption rates were modeled logistically dependent on the relative toxin concentrations. The general logistic rate model is given as a function R of x and m, where x is the concentration of interest and m is the maximum rate. Based on previously determined values from literature, k and b were arbitrarily chosen as 0.6 and 6 respectively. Corresponding equations to compute all rates are provided. To develop the appropriate values for each parameter, a literature survey was conducted. The concentration of lead in chocolate, P, was given as 0.062 micrograms per gram. The lead fecal excretion rate, F, was calculated as 0.7936 per days by multiplying the average fecal excretion rate times the average fraction of food consumed, that is chocolate, times the lead concentration in chocolate. The maximum rate of absorption of lead into the bloodstream, alpha max, was provided as 9 per days because all lead consumed must be either excreted or absorbed in the bloodstream within 9 hours of consumption. The maximum rate of transport between lead and the bloodstream and soft tissue, beta AS and SA, were determined to be 4 and 3.3 per days respectively. These values were chosen to satisfy the conditions such that the total concentration of lead in soft tissue compartments varies between 1 to 2 parts per million. The maximum rate of transport between lead in the bloodstream and the hard tissue, gamma AS and gamma SA, were determined to be 1 and 0.3 because 90% of the lead burden in the body is in the bones, and the rate from bone storage to the blood is not physiologically significant. The minimum and maximum renal excretion rates, R0 and R1, were determined to be 3 and 6 per respectively because lead has a half-life of 28 to 36 days in the blood. Several constraints were imposed on the model to prevent logical discrepancies. To ensure the existence of a solution without the application of the Fredholm alternative, the M matrix cannot be singular. Net absorption rates were defined for beta and gamma, provided the toxin concentration in the bloodstream and GI tract were greater than 0. As part of the natural detoxification process, the rate of toxin diffusion out of the bloodstream must be greater than the absorption rate of toxins into the bloodstream. For such conditions, the contaminant concentration in each body system was established at 0. The system of differential equations was solved with a numerical approach using SageMath, an open-source mathematical programming language. A Runge-Kutta fourth-order approximation was applied with a step size of 0.1 to generate 33,650 discrete approximations for the solution. Interpolation was conducted with splines to generate smooth, approximate solution curves. The chocolate consumption function C was modeled as a sinusoidal input where the amplitude was calculated based on the total amount consumed per day. A periodic weekend binge function was also developed to represent the increased chocolate consumption on the weekends. The sinusoidal amplitude were calculated for low, moderate, and high daily consumption rates of 10, 20, and 50 grams per day to account for increased consumption during traditional American holidays and birthdays. An additional step function was added. To represent varying holiday consumption patterns, the long and short-term models were developed. The long holiday model accounts for increased consumption spaced over several days, whereas the short model demonstrates a sudden spike during a single day. These functions were developed to provide recommendations to parents on the effect of spacing out their children's treats versus allowing for a binge.
With the model parameters and input functions developed, plots were generated from various solutions using matplotlib. The first input function we considered was the weekend consumption function that has a high enough amplitude to make the daily average of chocolate consumed 10 grams per day in the lowest case and 50 grams per day in the most extreme case with the short holiday model. In each plot, all dependent variables are plotted against time. M is given in blue, A is given in purple, S is given in red, and H is given in green. The solutions are roughly sinusoidal in nature with peaks on the holidays. In the case of the 10 gram per day average, the maximum lead concentration in hard tissue is 1.4 micrograms per deciliter, and it oscillates around 0.7. In the 50 gram per day average, the maximum peak is at 5 micrograms per deciliter and oscillates around 3.5. Next, we consider the same input function with the long holiday model instead. This has a major effect on the qualitative behavior of the solution curves by lowering the maximum peaks observed in each case. In the 10 gram per day average, the maximum peak is at 1.3 micrograms per deciliter and oscillates at around 0.65. And the maximum peak of the 50 gram per day average is reduced to 4.0 micrograms per deciliter and it oscillates around 2.8, a significant decrease from the short holiday metrics. The second input function we considered was a sinusoidal input, which may represent someone who resorts to chocolate as a way of coping with stress. For example, a person may not consume chocolate on Monday because they're not stressed, but as the week progresses, they become more stressed and consume more chocolate. Over the weekend, they de-stress and the week starts over again. In the 10 gram per day average with the sinusoidal input with a short holiday model, the maximum peak is 1.2 micrograms per deciliter and oscillates around 0.7. In the 50 gram per day average value, the maximum peak is at 4.2 micrograms per deciliter and oscillates around 3.3. We also considered the same input function with long holidays instead. As you can see, this made very little qualitative difference on the behavior of the solution, unlike in the weekend binge function. This is because in the weekend binge function, it is zero everywhere except for on the weekends, so any non-zero input that is not on the weekend has a significant contribution to the qualitative behavior of the solution curve. The long versus short holidays play a big role there because there is non-zero input over more days. In the case of the sinusoid, it's at only zero at very few points, so the long versus short holidays do not play a significant role in the behavior of the solution. It is almost entirely determined by the sinusoid itself. Finally, we considered birthdays, which were modeled as a step function of size 200 grams per day. These functions perturb the qualitative behavior of the solution. Of the dates considered, the most interesting is the December 21st birthday, which does not allow the model to reach equilibrium before Christmas. As such, the concentration of lead in the bones is elevated through the holiday.
Now let's talk about our results. Based on the CDC guidelines, a blood lead reference value of 3.5 micrograms per deciliter has been established to identify a baseline risk factor for lead poisoning. Comparing the model soft tissue and blood concentrations to this reference, maintaining chocolate consumption below 50 grams per day can prevent individuals from developing dangerously high lead concentrations. While binge consumption during holidays leads to a dangerous spike, spacing out the same quantity of chocolate over several days leads to the same average concentration. As such, we recommend parents to limit their children's daily intake of chocolate to 10 grams per day at most, and space out treats for holidays and birthdays to prevent brief but dangerous spikes in toxicity. As daily and weekend consumption plays the greatest role in average concentration, birthday proximity to other major holidays does not contribute as much as anticipated. Several limitations of the model must be considered. The box diagram does not accurately represent the human body with only 4 abstracted systems. The chocolate consumption patterns, such as the sinusoidal functions and the weekend consumption function, also cannot perfectly represent when a normal child would consume chocolate. The differential equations we chose are based on a simplified biological diffusion model. Model parameters remain fixed and were arbitrarily selected based on literature. However, in reality, these parameters may vary due to more complicated factors. Finally, the model assumes an average body weight and height and does not account for variable volume when determining toxin concentrations. In the future, it would be beneficial to implement a stability analysis of the current model to determine autonomous stability of the system. In this analysis, only lead consumption was assessed. However, there are some other concerning elements that can cause harm when ingested, such as cadmium and arsenic. From our model, we realized that when chocolate consumption is moderate, large spikes in consumption are most concerning. Therefore, an analysis of acute symptoms of heavy metal toxicity should be conducted. Finally, the model could be expanded upon to analyze the effects of more extreme cases of heavy metal consumption. Thank you for watching.